Alright, hey guys, this is section 5 of chapter 7, and this will be the final section for chapter 7, and we're going to be talking about specifically recursive formulas. We've talked about explicit, and explicit formulas we use for our sums, and typically you always just use explicit formulas, but there's a second type of formula called recursive. They're not as useful, but we will cover them real quick. But recursive, they only work when you're given ace of 1. So you have to have the value of ace of 1 for a recursive sequence to work, whereas an explicit will always work. And so that's why recursives aren't as useful as the explicit. Okay, before we get to the recursive formula, we're going to write the first 6 terms of each sequence. Okay, so given here on A, it says ace of 0 is 1, ace of n is equal to ace of n minus 1 plus 4. Okay, and this is actually considered a recursive formula like I mentioned up above. Okay, so since I know what ace of 0 is, then I can find ace of 1. And ace of n minus 1, we're used to plugging in n, but it's actually referring to the specific term. So if I have ace of n minus 1, that's the previous term, which is ace of 0. So ace of 0 would be plugged in here plus 4. So ace of 1 would be equal to 1 plus 4, which is equal to 5. Okay, then I'll use ace of 1 to get ace of 2. You use the previous term to get to the next. So ace of 2 will be equal to ace of 1, because if I do ace of n minus 1, that's 2 minus 1 plus 4, so this is really ace of 1, and ace of 1 is 5, so 5 plus 4, so ace of 2 is 9. And then I'll use ace of 2 to get ace of 3. Okay, so ace of 3 is equal to ace of n minus 1. Now that we kind of got that idea, which that would mean ace of 2, so 9 plus 4, so ace of 3 is 13. Ace of 4 is equal to our previous term, ace of n minus 1, which would be 13. That's ace of 3 plus 4, so we'll have 17. And then ace of 5 will be equal to 17 plus 4, 21. Ace of 6 will be equal to 21 plus 4, so 25. And you can see this is a long, tedious process to get all these, and you must use previous term to get to the next term. It's basically like you have the series written out itself. Okay, so our first 6 are 1, 5, 9, 13, 17, 21, and 25. Okay, on B here, B, this is a geometric. This one up here we add 4 each time. That was arithmetic. But geometric, we're multiplying 3 times f of n minus 1. And it gives us f of 1 is equal to 1. So I already know 1 is our first term. If I want to find f of 2, then I'll have 3 multiplied by f of 2 minus 1, which is really just f of 1. So 3 multiplied by 1. So f of 2 is 3. And then I'll just go up to f of 3 so that we don't overkill the process. But f of 3 would be equal to 3 multiplied by f of 3 minus 1, which is the same thing as f of 2. F of 2 we found previously, which is 3. So 3 times 3 is equal to 9. And you can see if you wanted to speed up the process, I can see my common ratio is 3. So I have 1, 3, 9, just multiply by 3, right? Continue to do that. So I got 27, 81, I believe. And then that's as far as I'll go in my head. Okay. So then it would continue to multiply by 3. Alright, now recursive, I mentioned earlier, it only works if you're given the first term, ace of 1. We're used to seeing arithmetic, where we do, explicit, where we do such as ace of 0 plus common difference times n, or of geometric where you take a sub 1 multiplied by your common ratio to the power of n minus 1. These are the ones we're familiar with so far. Now recursive, the arithmetic and geometric formulas are all different. For arithmetic, it's a sub n is equal to the difference plus the previous term, a sub n minus 1. Okay, and a sub n minus 1 really just means the previous term. Okay, and the geometric is a sub n is equal to that a sub n minus 1 previous term multiplied by your ratio, which makes sense, right? Because you continue to multiply by your ratio each term. And arithmetic makes sense as well because you continue to add that common difference to each term. Okay, so they're pretty self-explanatory with where they came from. Now let's write a recursive rule for 3, 13, 23, 33, 43. So it looks like you're adding 10 each time. So this would be arithmetic. So knowing that it's arithmetic, we have a sub n is equal to our common difference, which would be 10. So 10 plus a sub n minus 1, given that we know a sub 1 is equal to 3. All right, our first term here is 3. So then here's our recursive. Okay, next one here we have 1640 to 100. If I do 40 divided by 16, that's 2.5. So I can see we're multiplying by 2.5 each time. And even if you divide these two here, 625 and 250, you'll get 2.5. So then a common ratio is 2.5. If we're multiplying, this will be geometric. Okay, so I'll have a sub n equal to my a sub n minus 1 multiplied by my common ratio, which is 2.5. Given that a sub 1 is equal to 16. Alright, example 3 we're going to skip. Example 4, I'm going to write a recursive rule for a sub n equal to negative 6 plus 8n. Okay, so this is an explicit form that we're used to, but now we're going to change it to recursive. Okay, so to get the recursive rule, we'll need to know what a sub 1 is. So we can just plug in a sub 1 equal to negative 6 plus 8 times 1, which is negative 6 plus 8. So a sub 1 equals 2. Okay, knowing that a sub 1 is equal to 2, then we can write the recursive a sub n would be equal to your difference, which the difference would be multiplied by your n and your explicit formula. So the common difference is 8. So then we have 8 plus a sub n minus 1. That previous term, going back to the recursive formula. And then if I wanted to verify that it works, a sub 2 is equal to negative 6 plus 8 times 2, which is 1610. So then to verify this really quick, we'll plug in a sub 2 into this formula, or recursive, and we'll get 8 plus 2, which is 10. So I get the same. Because our a sub n minus 1 is 2, our previous term before a sub 2 is a sub 1. And it all checks out. Okay, on B here, we're going to do the explicit for this geometric to the recursive. Now this is a little nicer because the explicit for geometric is a sub 1 multiplied by your ratio to n minus 1. So we're given a sub 1 right in the explicit formula, so a sub 1 is negative 3, and your common ratio is also given right there. R would be 1/2, so you'll have a sub n equal to your common ratio, which is 1/2, multiplied by a sub n minus 1. Alright. Write an explicit rule for each case. So now we're given the recursive. Now we're going to go back to the explicit. Okay, so it gives us a sub 1 is equal to negative 5. And then our recursive is a sub n equal to a sub n minus 1 minus 2. So to get back to my explicit, we need a sub 0. Okay, because my explicit formula for arithmetic is a sub 0 plus my common difference multiplied by n. Okay, and it looks like my common difference here is negative 2. Because our common difference is at base and 1 minus 2, so d is equal to negative 2. So I already know that's going to be negative 2n, but now we need to find a sub 0. Okay, to find a sub 0, honestly, I'm just going to use the idea that our common difference is negative 2. So to go backwards from a sub 1, I will add 2. So a sub 0 will be negative 3. So then my explicit formula will be a sub n is equal to negative 2n minus 3. If you wanted to make sure that it worked, you could plug in 1, get negative 2 multiplied by 1 minus 3. Negative 2 minus 3 is your negative 5. Okay, b here, we have a sub 1 is equal to 10, and our recursive is a sub n equal to 2 multiplied by a sub n minus 1. So our common ratio is 2. So to go to my explicit, it's actually pretty simple because it gives us a sub 1 minus 10. That's what we need for our explicit and our geometric. So you take your a sub 1 minus 10, a sub 1 equal to 10, and 10 multiplied by 2 to the n minus 1, your common ratio, r to the n minus 1 power.